All right, let's talk about one of the most frustrating challenges in the lab, matrix effects. Getting this right can be the difference between data you can actually trust and, honestly, months of wasted work. So today, we're going to build a practical framework to not just diagnose these problems, but to engineer robust solutions right from the start. Let's get into it.
Does this sound familiar? You've run your assay, everything looks perfect, but your replicates are just all over the place. That high CV, that high coefficient of variation, it isn't just random noise, it's a signal. And it's often the very first sign that something hidden deep inside your sample is wreaking havoc on your results.
And yeah, that something is almost always matrix effects. I love this quote from the source material because it totally reframes the problem. These aren't some rare, weird things that happen once in a blue moon. They are an inherent, expected part of working with complex biological samples. So the key isn't to avoid them, because you can't, but to understand them and, more importantly, control them.
So what exactly are we up against here? Let's take a minute and really break down what matrix effects are and where they come from. Okay, at its core, a matrix effect is just when something other than what you're trying to measure interferes with that measurement. It's all the other stuff in your plasma or your serum or saliva that just gets in the way. It can either hide your signal, that's suppression, or it can artificially boost it, that's enhancement. And this is why your carefully made calibrators, which are in a nice, clean buffer, behave completely differently than your real-world samples.
And the reason they're so tricky to pin down is that this interference can happen in so many different ways. I mean, we're talking about everything from random proteins just sticking to your plate, to antibodies in the sample itself, cross-reacting with your reagents, or even enzymes in the sample literally chewing up your target before you can measure it. It's a really multifaceted problem.
Okay, so we're pretty sure we have a problem. How do we even start to diagnose it? Well, luckily, there are two classic go-to tests that really form the foundation of any good investigation. These are your two main tools. Over on the left, you've got dilution linearity. This test basically tells you if you have a problem by checking if the sample behaves predictably as you dilute it. Then on the right, spike recovery tells you how accurately you can measure a known amount of your target when you add it into the sample matrix. But here's the crucial part, and you see it right at the bottom. They are fantastic at telling you that a problem exists, but they can't tell you why.
Now, what's really cool is how you can read the story your dilution data is telling you. If the calculated concentration of your analyte seems to go up as you dilute the sample, that's a classic sign of signal suppression. Something in that concentrated matrix was hiding your target. If the concentration goes down more than it should, you're seeing signal enhancement. And if it does both, goes up then down or something weird like that, well, you've got a really complex problem on your hands.
Now for spike recovery. This is the magic window you're usually aiming for. If you can find between 80 to 120% of the stuff you spiked in, that's generally considered an acceptable range for a lot of assays. If you're way below 80%, something's probably causing low recovery, like a binding interference. But if you're above 120%, you might have something in there cross-reacting and amplifying your signal.
And this brings us to such a critical point. A lot of people, and maybe you've done this too, they stop right here. They diagnose the problem, they document it, and they just try to live with it. But as the source material points out, this is a huge missed opportunity. Identifying the problem, that's just step one.
So how do we get past just finding the problem and actually solve it? Well, this is where we need to shift our thinking from simple testing to true system engineering. And we do that using a really powerful tool called design of experiments, or DOE.
Instead of that slow, painful process of changing one factor at a time, testing a new buffer, then a new incubation time, then a new detergent, DOE lets you test all of them at once in a really structured way. And this isn't just faster, it's so much smarter because it's the only way to see how all these different factors actually interact with each other.
Let's look at a quick example to make this real. Here's a simple screening design. We're testing 4 different things: the type of protein in our diluent, the type and concentration of our detergent, and our incubation time. A DOE experiment is going to structure all the runs so that we can clearly see the effect of each of these things and, most importantly, their combinations. And this is the real power of DOE, the secret sauce: understanding interactions. You might find that a certain blocker protein only works well when you pair it with a specific detergent. Changing one factor at a time would never let you see that relationship. It's these interactions that lead to the big breakthroughs in optimizing your assay. So all of this really brings us to the core message today. It's about a fundamental shift in how we approach assay development. We've got to move from being reactive problem solvers to being proactive system designers.
Just look at this comparison. The old way, one factor at a time, it's basically guesswork. It's so inefficient it wastes precious time and reagents, and you often completely miss the real root cause. The new way, using system design, is all about building robustness into your assay from day one. It's data-driven, it's efficient, and it gives you this deep understanding that leads to faster, more confident research.
So what does this new mindset actually look like in practice? Well, it builds into this really powerful iterative cycle. You start with those classic diagnostic tools, dilution, linearity, and spike recovery, to really understand the problem. Then, you use those results to make an educated guess, a hypothesis, about what's going on. Then you use DOE to systematically test it. You find and implement the best conditions, and, this part's crucial, you reevaluate to confirm you actually fixed it. It's this continuous loop of improvement that creates those bulletproof assays that produce reliable, publishable data.
So, we've covered the whole framework, from diagnosis all the way to a data-driven solution. But honestly, the learning doesn't stop here. The best insights often come from the community, from all of you.
Now, I really want to hear from you. How do you tackle this? What are your go-to strategies? Have you tried DOE, or do you have other clever tricks up your sleeve for taming those really difficult sample matrices? This is such a common challenge, and sharing our collective experience is truly how we all get better.
So please, drop your tips and any questions you have in the comments section below. If you found this useful, give it a like and maybe share it with a colleague who might be battling their own assay right now. And of course, don't forget to subscribe for more deep dives into the science behind our methods. Thanks so much for watching.